nature. But here we want to apply our derivatives to maximums and minimum values, and specifically critical numbers. A critical number of a function f is a number c in the domain of f such that either f prime of c is equal to 0 or f prime of c does not exist. Yep, we don't waste time here. So we have listed all these critical points here, and we're going to state why they are a critical point. Number one, this is an endpoint. And because it's an endpoint, you cannot take the derivative at that spot. Okay? So the derivative does not exist on an endpoint. The derivative exists from the right, but it does not exist from the left. Here, this is a critical point because the derivative is equal to 0. Here, the derivative does not exist because it's a corner, exactly. Can't take the derivative at a corner. So again, the derivative does not exist. That's a critical point because f prime of x is equal to 0. On the bottom, again, f prime of x is equal to 0. And at the end, that's an endpoint. We cannot take the derivative at an endpoint. Okay, everybody good there? So, as we consider these, we're not going to necessarily find these today, but we have what we call absolute maximums or global maximums and absolute minimums or global minimums. And I'm going to list here what the absolute maximum is within this piece right here. The absolute maximum happens where the largest output is on the graph, and that'll be right here. So at C sub 4 is where our absolute maximum occurs. Where does our absolute minimum occur? C sub 1. A local maximum, the really raw definition of it, this is not a great definition. We don't like to say these things as mathematicians, but we will. It's when you get to a spot on the graph where it's the largest value for those immediately around it. So if I look at this spot right there, it's the largest value for those immediately around that area. So C sub 2 is a local maximum. It is also true that C sub 4 is a local maximum. You could be a local maximum and a global maximum. You could be both. Okay. Local minimum is going to be C sub 3 and C sub 5. Notice that the local minimum occurs at this corner or where the derivative is equal to 0. And notice that all of these represent some of our critical points. Okay? So critical points are important because we try to find maximums and minimums. Maximums and minimums. So we looked at those and we defined those. Why don't we go to Fermat? Fermat, great mathematician. We won't go into his world or his mind. But he basically said this: if f has a local maximum or minimum at point C, and if the derivative exists, then we can say something important, and that is the derivative is equal to 0. Local maximums and minimums happen when the derivative is equal to 0. So, critical points. We've talked about this type of stuff a little bit before, but first give you an example. If we have that type of shape, we say that this is a critical point because the derivative is equal to 0. And notice that we have a local maximum and a local minimum at that spot. Everybody good with that? If you have a graph that has a corner, like an absolute value function, we could say that the derivative does not exist at that spot. And that is a critical point. Suppose that we have a graph that looks like this. It says vertical tangent. What do you think of when you hear that phrase vertical tangent? Good, up. What about up? Undefined slope. So because the slope is undefined, that is a critical point as well. This is not an example of a critical point, and I'll show you why. Suppose you have a graph that looks like this, with this vertical asymptote at x equals -2. We don't say that that's a critical point because -2 isn't even part of the domain of that function. See what I'm saying? So, can you take the derivative at -2? No. But is there even a function output at -2? No. So, while it's an interesting spot, it's not considered a critical point. So our goal today is to be able to find the critical numbers of these functions. Confirm the critical numbers by sketching a graph of the function. We don't have to do that, but we sure could. All we do is we take the derivative and we set it equal to 0, or we look where the derivative does not exist. What is this derivative? I want to set that equal to 0. Does it factor? Yes, it does. 3x and x. I have a -1 and I have a -1. So x equals 1/3 and x equals 1 would be the places where this derivative is either equal to 0 or it does not exist. In this case, it would be equal to 0. Not too bad, right? So you'll practice taking derivatives and look for these. What rule would you use here? Quotient rule. First of all, I just want to say, what is the domain of this function? X cannot be equal to? 0, because that would produce 0 in the denominator, right? 1 produces 0 in the numerator, which is just fine, but I can't have 0 in the denominator. So I'm going to go ahead and take that derivative. Derivative of the top is 2x times the bottom minus the derivative of the bottom, which is 1 times the top, x squared minus 1. And that all sits over x squared. And so f prime of x is equal to 2x squared minus x squared plus 1. All over x squared. 2x squared minus x squared is 1x squared plus 1 over x squared. And so I ask you, when is the top equal to 0? If I plug in -1, -1 squared is 1 plus 1 is 2. So -1 is not a spot where it's equal to 0. Square root of 1 is 1. 1 squared is 1 plus 1 is 2. Yeah, x squared plus 1 is always positive, right? This is the top is never equal to 0. When is the bottom equal to 0? At 0. And is that part of our domain?
Right.
So it's not part of our domain, so therefore we have no critical points. Take out your calculator. A calculator in this economy?
Right?
This economy, right?
Who can afford one?
Right?
Exactly.
You steal it from your sibling, that's what I did. What you gotta do in this economy?
This economy, man.
Yes.
Resort to thievery. I type in x squared minus 1, and I divide it by x. That's my original function. I want to examine that function and see, is there a spot where it has a critical value? I look at the graph. Is there ever a spot where the derivative is equal to 0 as you look at that graph? There's not. Is there ever a corner? No. there's a spot where you can't take the derivative, and that would be at 0, but that's not part of the domain anyway, so therefore, no critical points. So you can always sketch a graph and say, is that something that has a critical point or not? All right, let's turn back to my annotate.net. Where are you? Where'd you go? Somebody? I logged out, didn't I? I did, yep, let's go back.
What do you think that one?
I think we're gonna put out like a secret code.
CIA?
The CIA rats, like we were talking about in the first
Oh my gosh.
I definitely know it's not.
Do you think we're a part of Trump's cabinet?
Maybe, maybe it's for Hamlin, and they didn't write it down because they knew you were gonna show up.
Hey,
That
why
is a
would
good
we
point.
show up?
Hey, Hamlin's a good school.
Yeah, Hamlin's actually
you-
the oldest know Minnesota. Did
It
you
is.
know that?
Yeah.
I did.
Yeah.
It
Are you
is-
going?
I don't know where I'm going. Bree.
Yeah, maybe we want to keep our options open.
Right.
All right, for this one, I'm not even gonna find the derivative, because I know something about the function. What does the, where does the absolute value function look like? Yeah, we just simply wanna find where this spot occurs, right? And so I'm going to factor out an absolute value of 3. What is the absolute value of 3? 3. So I have 3 times the absolute value of x minus 2. So that tells me that this function, the absolute value function, is shifted where?
Right.
To the right 2 units, okay? So if that's what the graph looks like, where does the derivative not exist? At 2. So x equals 2 is a critical point. I didn't even take the derivative. I knew that if I take the derivative at that spot, it doesn't exist because I have a corner. Let's look at one that we don't know the graph of. If you guys do know what that graph looks like, that's impressive because I've really got no idea. I have the square root of x cubed minus 2 roots of x. As we think about this, talk to the person next to you real quick. What do you think is the domain of that function? Talk, what is the domain of that function?
I don't really know.
So you know the graph looks like that's what it is, right?
Negative what?
Not much more. Oh, negative.
Instead of turning it to 2, you can draw a circle.
They can't be square.
Can you schedule?
Yeah, you can schedule it. What time would we be there? Should we,
Y-intercept is negative 1.
should we set it for like, we get out at what time?
11:44.
40, 11,
We're probably
Yeah,
here.
that
We
line
should maybe
crosses
set
the
that
line.
11:45.
Maybe it's like all the numbers.
Yeah.
I don't even know if they go
Put my name on it?
Yeah,
So
Bree.
x squared times x is x cubed.
I definitely
That's
know it's
positive.
not for something about
So it ties up.
tiles.
Because it's odd,
Like
it starts
leadership,
as an
because
opposite.
I got one of these. So, no ma'am.
Tiles of leadership.
What's
It's
title?
negative.
You know, like the
Leadership?
things in the cafeteria, one of those tile.
Odd starts as an opposite.
Oh,
That ain't this.
The wall?
you got a wall of inspiration.
No.
X
What are
cubed.
you, fucking tiles of leadership?
Yeah.
Are you referring to the wall of
Yeah.
Oh, the
inspiration?
tiger thing. And
This is the fourth.
tiger.
So
What, I don't know, I don't, what is that about?
Tiger.
What are you doing, what are you doing with that? I don't understand.
No.
So
Create your own bowl. Is that what we're doing?
notice that it's a negative.
Yes.
Therefore it comes down.
Hey,
Because it's
get to
even,
know
it starts in X.
I think I'm going all out today. Grilled
Hey,
steak.
Jacob, join boys swim or else they don't have a team of it's even if others in the same.
Odd opposite direction.
Is there nobody in boys swim? What?
Yes, no.
Okay,
No way.
thoughts on the domain?
I really.
Negative. You wear Speedo.
Can't be
Close.
zero.
Numbers.
Can't be 0.
It can be 0. It can't be negative numbers. Why can't it be a negative number? You can't take the square root of a
Negative.
negative. So therefore, the domain is from 0 to infinity. So as I compute these critical values, I should come up with values that are somewhere between 0 and infinity, okay? But 0 is included in the domain, because if you plug in 0, you get an output of 0. I know that this graph, one thing I know about it is it goes through the origin. I know that for sure, okay? So let's go ahead and take the derivative here and see what we come up with. I have f prime of x is equal to, I'm going to rewrite this instead of x, or root of x cubed, I'm going to raise x to the 3/2 minus 2x to the 1/2. What is the derivative of x to the 3/2?
3/2 x to the -1/2.
To the positive 1/2,
+1/2, JK.
Wait, why?
right? 3/2 minus 1 is 1/2.
Right.
Minus, then 1/2 times 2 is 1, and so I get x to the
-1.
-1/2. Good job. So in other words, f prime of x is equal to 3 over 2 roots of x minus 1 over the root of x.
Why would that square root be on the bottom?
Yeah.
Oh, sorry about that. Yep. So 3 roots of x over 2. Good. The best way to navigate these waters is to make sure that you write it as one fraction, find common denominators. What is my common denominator? So I have 0 is equal to, I'll multiply top and bottom here by the root of x, and the top and bottom here by 2. And so what I get in the top is 3x minus 2. And the bottom, I get 2 roots of x. Where is the bottom equal to 0? At 0, right? Is 0 part of our domain? It is. So 0 is a critical point. Where is the top equal to 0?
2/3.
At 2/3. So if we examine this graph, we should see that the derivative does not exist at 0 and that the derivative does not exist at 2/3. Take out your calculator and let's see if we see that as we graph it.
Let's figure this out.
We have the square root of x raised to the 3rd power, and we have minus 2 roots of x. I'm going to zoom as a decimal because I have a general idea of what this does look like. And that's our shape. You can't take the derivative at 0. Why? It's an endpoint. Notice how it found the endpoint, which is pretty cool. And then as you travel along that graph, as I move this direction, the derivative is equal to 0 at an x value of about 2/3. See 0.6 to 0.7 right in there, 0.6 repeating. That's where the derivative is equal to 0. It found those 2 points. So I know that we can press graph on our calculator, but just for a second, put yourself in the situation of Isaac Newton, who's sitting back in the 1500s saying to himself, what does this graph look like? And he wants to come with some interesting information. Doing some of these tests could really produce what he wants, which was super helpful. Okay, flip it over, and we'll pick up here on Monday. But right now, you guys can turn to your homework. I think I passed that out.
There's gonna be no homework.
And at the very minimal, you should be able to work through problem 5 or 6.
Oh.
Some of the ones that are a little bit more challenging, we might have to see an example or 2 more, but you should be good to go. So you guys can work from there.